Hello and welcome back to the Unit 5 review videos. Today's video is going to be on the second half of Unit 5 Sequences and Series. In the first video of this unit, we did the video overview, lesson overview, looked at the Common Core standards associated with the Unit 5, the formulas, and also some topical reviews. So if you want to see how to do any of these, have a little bit of review on the very basics of arithmetic and geometric sequences, and finding the nth term and so forth, go back to the video 1 to see that review. In this video, we will go over finding the equations of sequences given non-consecutive terms. We'll look at summation notation, some work with series, mortgage payments applications, the formulas for those, and then we're going to sum up the most important aspects of the lesson, of this unit. Things you should be able to do after this unit. So let's get into some topical review. Sometimes you're going to be asked to find the formula for the nth term of a sequence given two non-consecutive numbers in the sequence. Now it will tell you whether or not it's arithmetic or geometric, so make sure you note the differences. To do this, to write the equation for the formula for the nth term of a sequence, we need to know the first term and the common difference. Okay, so we have to work this formula in ways to help find out those pieces of information. So recall that the formula for the nth term of an arithmetic is the first term plus n minus 1 times the common difference. Okay, we're going to use that to find the formula. I know the sixth term in this example is 22, and the 10th term of a particular sequence is 38. So what helps me is to write place values for each of those terms. Okay, I don't know what the 7th, 8th, 9th term are going to be, or even the 5th, 4th, 3rd, first term. But I know the 6th term is 22, and the 10th term is 38. In an arithmetic sequence, what you're doing is you're adding the same number to the previous term to get to the next term. So essentially I'm adding the common difference once, twice, 3 times, 4 times to get to the 10th term from the 6th term. So what that allows me to do is to solve for the common difference. Is starting at the 22, I'm adding 4 of the common differences to get to my 38. I can set up that equation to solve for the common difference. Subtract 22, I get 4d is equal to 16, so the common difference in this case is going to be 4. I know one piece of information I need in the formula. I just need to find out what this first term is going to be. To do that, I'm going to use whichever term I want to, either the 10th term or the 6th term, coupled with the common difference we just found, to find out the first term. For some reason for me, the first of the two, or lower in the sequence, the earlier in the sequence is usually what I go to first, but you could use the 10th term as 38. Okay. So if I use the 6th term as 22, that means that the 22 is found by taking the first term, which we don't know yet, added to 6 minus 1, because n is 6 there, times 4. Okay, notice here, solving this equation, I can solve for that first term. So if I keep going, I get 5 times 4, which is 20. Subtract the 20 from both sides, I have a first term of 2. Now I can write my formula for the nth term of this sequence. So the nth term of the sequence is going to be the first term, which is 2, plus n minus 1 times common difference of 4. Notice I could now write this in the recursive form as well. I could say a1 is 2, and an is the previous term, adding 4. The recursive form is actually pretty nice in a sense that it shows how it's arithmetic. You're adding forward to the previous term. That's what an arithmetic sequence is created by, adding the same number to each term to get the next term. To find the formula for the nth term of a geometric sequence, we're going to do the same kind of idea. We need to find out the first term and the common ratio in this case. Okay. I'm going to write the place values, the third, the fourth, the fifth, the sixth, and the seventh. I know the third term is 1600, or 1060, and the seventh term is 655.36. Now in a geometric sequence, I'm going to be multiplying each term by the common ratio to get the next term. So I'm multiplying by r 1, 2, 3, 4 times. So that means whatever I start off with, in this case 1600, I'm going to multiply by r 4 times, or in other words r to the 4th power. That should give me my seventh term, which is 655.36. Divide both sides by 1600. You get r to the 4th is equal to 0.4096. Recall our work with exponential equations and exponential functions. Is that to solve for r, I want to raise up both sides to the reciprocal power, so raise this to the 1/4 power, because then I can multiply those exponents to give me r to the 1st, which is what I'm looking for. So if I raise 0.4096 to the 1/4 power, now be careful when you type this in with your parentheses, make sure you have parentheses 1/4 as the power. I get 0.8 is my common ratio. Alright, now I know the common ratio, I just need to find my first term. I'm going to use the third term as 1600, but you could use the seventh term if you choose. So the third term is 1600. So the 1600, which is the third term, must be equal to whatever the first term is, times the common ratio, which we just found is 0.8, raised to the 3 minus 1, because of the third term. Okay, so 1600 is equal to a1 times 0.a to the second power then. Continue to solve this, we get 1600 is equal to a1 times 0.64. Divide both sides by 0.64. I get an initial value, or the first value in the sequence, of 2500. Now I have everything I need in order to write the formula. So I'm going to write in both forms, in the explicit form and the recursive form. So the explicit form, the nth term is going to be the first term, which is 2500, times the common ratio raised to the n minus 1th power. In the recursive form, I'm going to do this one in terms of function notation. I could do it with the a notation, but I'm going to use the function notation. The first term is 2500, and the nth term is found by taking the previous term and multiplying it by 0.08. So I'm going to write 0.08 times the previous term. Let's move on to summation notation. Summation notation, this capital letter stands for S, which is sigma in Greek letter. It just means you're adding. Okay. And you're adding a bunch of expressions where you substitute, this k is called the indice, the index. It's usually k, I, j, or n. Okay. Ooh, and I meant to write this. This should be a k squared. Okay. You are going to substitute all the values beginning with this number on the bottom all the integers from there up to the top number. Okay, so negative 2 to 3, I have negative 2, negative 1, 0, 1, 2, 3. I have 6 different values I'm going to be adding up in the long run, okay, because I can plug in 6 different numbers. Starting with the negative 2 in this particular example, I get this. I'm going to add it to the next number in the and from k up to positive 3 is going to be negative 1. So I'm going to plug in negative 1 in place of the k. Then I'm going to plug in the 0 in place of the k. Plug in the positive 1. Plug in the positive 2. Plug in the positive 3. And I'm going to stop at whatever the value in the top is going to be. Okay. But that's what a summation is. You're just summing up a bunch of different values by plugging in from the lower index value up to the top. Let me clean this area up just so it looks a little nicer. So again, this should be a k squared plus 1. Alright, and then you just got to simplify and find out what the sum's going to be. So this gives me 4 over 4 plus 1 plus 4 over 1 plus 1 plus 4 over 0 plus 1. And I would take your time with these. I mean, obviously you don't want to run the risk of making mistakes. Take your time. Don't just rush to the answer. Okay, and continue to simplify. I get 4 over 5 plus 4 over 2 plus 4 over 1 plus 4 over 2 plus 4 over 5 plus 4 over 10. Now, notice some of these we can simplify nicely. We can simplify the 4 over 2 to become a 2, the 4 over 1 to become a 4, sorry, and then this becomes a 2. 4/5 stays 4/5, and the 4/10 actually simplifies nicely to 2/5. Combining all the integers in this case, 2 plus 4 plus 2 gives me 8. The 4/5 plus 4/5 plus 2/5 gives me 10/5. Oh, this ends up being really nice. 8 plus 2, which is 10. So this summation has a value of 10. Now notice in this particular example, when I was dealing with fractions that I didn't have to find really too much of a common denominator for. They all simplified to a denominator of 5 in the long run. However, you could rewrite all the denominators so that all the fractions so that the denominators are the same before adding them together. If you were to do that, notice in the common denominator between all of these is a 10. So I could have rewritten it as, so I'm just going to erase this on the bottom just to show how you could have done common denominators. I could have rewritten it as 8/10 multiply top and bottom by 2 plus 20/10 plus 40/10 plus 20/10 plus 8/10 plus 8/10 is in the 4/5, so plus 4/10. 1, 2, 3, 4, 5, 6. Negative 2, negative 1, 0, 1, 2, 3. That's 6 values. Okay, it covers everything. And if I were to add all those numerators, 2 plus 20 plus 40 plus 20 plus 8 plus 4, notice that gives me 100 over 10, which is 10. Another way to validly find the answer. Now let's get into series. A series is just a summation. Okay, so an arithmetic series is just the summation of all the values, or a certain number of values, in an arithmetic sequence. Okay. So it's just a sum of the arithmetic sequence values. And this formula, as I mentioned earlier, is not given to you on the Regents exam, so make sure you memorize it. But you take the number of terms multiplied by the sum of the first and the last divided by 2. So to find the sum, or the series of this sequence, let's say of -7, -5, -3, find the sum of the first 20 terms. I'm essentially finding the -7 plus the -5 plus the -3 plus ... all the way up to the 20th term. So sometimes you have to work this sequence formula to find out the last term. Because in this form, in order to find the sum of the sequence, to find the series, I have to know the number of terms, which I know is 20 in this case. The first term I know is -7, but I need to know the last term in the arithmetic sequence. So I have to actually find the 20th term. The formula is the first term, which is -7, plus n minus 1, which is going to be 19, times the common difference. Now notice the common difference, what am I doing each time? I'm adding 2 to get to the next term. So 19 times 2 gives us 38. So -7 plus 38, which gives us 31. So the 20th term is going to be 31. Now I can find the sum of the sequence. So the sum of the first 20 terms, as 20, is going to be the number of terms, which is 20, times the sum of the first and the last, so -7 plus 31, divided by 2. What I think is really helpful is to find out what the first and the last term add up to before simplifying it further. And then we can calculate 24 times 20 divided by 2, which is 240. So the sum of the first 20 terms in the sequence is 240. Now, I could have done the long way and listed them all the 20 terms up and used my calculator to add them up, but it's easy to make mistakes that way. Okay, but it's never a bad idea to go that way in case you forget. Now let's look at a geometric series. Again, the idea of a series is that you add up the terms in a sequence. There is a formula that will be given to you in the reference sheet and is given to you in this format. Okay, A1 minus A1 times r to the n divided by 1 minus r. I personally like the formula where you factor out the A1, the first term. To me, that seems a little bit more logical to use, but both forms are the same equation. So if I want to find out the sum of the first n terms, I need to know the first term, the common ratio, and then the number of terms. So notice in the geometric, I don't need to know what the last term is going to be. I know the first term is 16 over 2500. I can find the common ratio by dividing any two consecutive terms. Now in this particular case, it might be easier to divide the last two, okay, because we're doing some crazy fractions in the beginning. So I'm going to do 1/10 divided by 1/25. Remember, with our work with complex fractions, is that I can multiply top and bottom by the reciprocal of the bottom, or by a common factor. Notice if I do that, then I just get 25 over 10, which is 2.5. So the common ratio is 2.5. And I know the number of terms is 7, so I have everything I need to in order to find the sum of the first 7 terms. So the sum of the first 7 terms is going to be the first term, which is 16 over 2500, times 1 minus 2.5 to the 7th power divided by 1 minus 2.5. If I do 1 minus 2.5 to the 7th power, that gives me a fairly lengthy number, right? You get negative 609.3515 625, all divided by 1 minus 2.5 is negative 1.5. So if I multiply that number, that negative 609.35, so forth, by 16 divided by 2500, right, the number's looking a little nicer. I got negative 3.89985 divided by negative 1.5. Which gives me 2.5999. So the sum of the first 7 terms is 2.5999. And that's how you find the sum of a geometric series. Trying to zoom in and out here, and I keep actually drawing stuff. Okay, so just ignore that. Now, one thing you should also be able to do is to write a series in summation notation. So let's say I'm given the arithmetic series, or the geometric series, or a pattern sequence. What you want to do for the arithmetic and the geometric is you want to essentially find the formula for the nth term. That's what you're really going to be using. Okay. So I know, and you need to know how many terms, by the way, there are as well. So I know that the first term of the arithmetic sequence is negative 5. The next term is negative 2. Next one's positive 1, positive 4. I might be able to clearly see my common difference here is positive 3. I need to find out how many terms there are, so I need to find out the n value associated with the 43. I'm going to use that arithmetic sequence formula to find out how many terms we have. So the nth term, which is 43, is equal to the first, which is negative 5, plus n minus 1 times the common difference, which is 3. I'm going to solve that for n. I have to distribute the 3 to both the n and the negative 1. Combine like terms, I end up having 43 is equal to 3n minus 8. Add 8 to the 43. I get 51 is equal to 3n divided by 3, 17. Okay, this is a fairly good number of terms we're adding up in that particular series. Alright, now I'm just going to rewrite this again. The nth term then is going to be found by doing negative 5 plus n minus 1 times the common difference, which is 3. I'm actually going to write this out so that there's no parentheses. Okay, I think it looks a little nicer if you do that. You don't have to, but it looks a little nicer if you do it. I get the nth term then is going to be 3n minus 8. So to write this in summation notation, I'm going to start it at 1 because the sequence starts with the first term, which is negative 5. And I'm going to go up to however many I have, so I have 17 in that sequence. So it's going to be 1 to 17. And what I'm going to write after the summation symbol is just the explicit form, the 3n minus 8. Typically we put parentheses around the 3n minus 8, especially if there's a binomial, or basically more than one term. but I'm sure you'd be fine if you forgot them. But try and put the parentheses though. There's a summation notation for that arithmetic series. For geometric series, you want to do the exact same thing. Okay. First, note that the common difference here, or the common ratio, is 2. You're multiplying by 2 each time. Times 2 times 2 to get the next term in the sequence that we're adding up. That looks like a plus 2. Get that again. Times 2 times 2. Won't write. There we go. Okay, times 2. So the common ratio is 2. I need to still know the number of terms in the sequence. So I'm going to use the explicit form to find out the number of terms. So I know that the nth term is 768. And it's going to be the first term, which is 3, times the common ratio, which is 2 raised up to the n minus 1th power. Now, when we're dealing with sequences and numbers, typically what you want to do is you want to use a method of common basis to solve, because a geometric sequence, you're always multiplying by the same thing, so you will have a common base. So let's divide both sides by 3 first to get the 2 to the n minus 1 by itself. So that gives me 256 is equal to 2 to the n minus 1. So let's get a common base. What power of 2 gives us 256? You might have to experiment a little bit with it. So if I try 2 to the 10th, I get 1024. That's a little too high. So let's try 2 to the 8th. And there we go. So this is 2 to the 8th is equal to 2 to the n minus 1. So that 8 must be equivalent to the n minus 1, because the same basis, the exponents must be equal. So that 768 is the 9th term. Now again, just like before, I'm going to find the sequence, the explicit form for the sequence. So the nth term is the first term, which in this case is 3, times the common ratio, which is 2 to the n minus 1. So right in the summation notation, I'm going to go from k equals 1 all the way up to 9, because there's 9 terms there, of the 3 times 2 to the n minus 1. There's your summation notation. Now one thing that's really nice to point out is that there isn't just one summation notation you can write. There's actually several. For instance, if I started the summation at 0, I would therefore go up to 8, because 0, 1, 2, 3, 4, 5, 6, 7, 8 is 9 values you're adding together. And if you were to do that, then I would have to start at 3, so I'd have maybe 2 to the k. Oops, I just noticed something. Be careful. Hopefully you caught this. This should be 3k minus 8. This should be 2 to the k minus 1. Make sure you change those appropriately. Okay, my bad. My apologies. Okay, but this, what I just wrote down here, is equivalent in value to that summation notation. It's just written in a different way. You'll get the same exact value. So just note that sometimes your notation might be correct even if it doesn't match what's in the answer key. Now for the pattern sequences, those get a little more challenging because you have to kind of find out what the pattern is going to be. And this one, what I'm noticing with this pattern is that each of these numbers are 1 away from a perfect square. Specifically, 2 is 1 squared plus 1. 2 squared plus 1 gives us 5, 4 plus 1. 3 squared plus 1. 4 squared plus 1. Okay, notice we go all the way up to 10 squared plus 1. So I go from k is equal to 1 all the way up to k equals 10. That's going to be my domain of inputs, essentially into the summation notation. I can go right to the formula now. So k starts off at 1, goes up to 10. And what I did is I've summed up the value of all the k squareds plus 1. Now when you're asked to write the formula, it's always a good idea to, whatever formula you get, whatever summation notation you get, work backwards to see if you get the original pattern. Okay. If you were to plug in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I should be getting all the numbers over here. Okay. So it's a good idea to check it in that way. The last thing we focused in this particular unit was the mortgage payments. Now, for all the resources I've seen, it seems like whatever formula they're going to ask you to use for mortgage payments, like the amount left on a mortgage, will be given to you in some form. Okay, because I've seen several different ways to write the formula for the amount owed on a mortgage, or the formula to find the monthly payments on the mortgage, or the number of payments given a certain monthly payment that you have left. Okay. But these are the formulas that we learned in class. Okay, these are not given to you. However, if you're one who loves to memorize formulas, this might be a good one to just know. Okay, but you do not have to memorize this. The amount owed on a mortgage after n number of payments was found by taking the principal and adding 1 plus the rate raised to the n minus m times 1 minus 1 plus r to the n divided by 1 minus 1 plus r. That was the formula we used to find the amount remaining after n payments. Just take a note here, this connects to geometric series because this right here, excluding the minus sign, is essentially a substitution into the geometric series, where m is the initial amount, which is going to be your monthly payments. The 1 plus r is your ratio, common ratio, and then there you have it. Okay? It's just important to note that. The formula we saw for calculating the monthly payment was found by taking the principal times the rate divided by 1 minus 1 plus the rate to the negative nth power. Again, you don't have to memorize it, but it's just good to see it in case you want to use it in some problems. And again, these problems will probably be most likely given to you. The last one was a little crazy. To find the number of payments left, dealt with logs, which is just rewritten form of this formula right here. That's just rewritten to find the value of n. And notice, because n is an exponent, you have logs you're going to be dealing with. I'll write it with common logs, but you can actually write it with natural logs as well. It's going to be the log, negative log of 1 minus the principal times the rate divided by m, all divided by the log of 1 plus the rate. Again, you don't have to memorize these formulas, but you could, for only a few number of payments on a loan. Say you know that the principal balance is $100,000, and you have a let's say a 6% interest. By the way, one thing that's really important to note is that this r, or this 1 plus r, is not 0.06 or 1 plus 0.06. This r is actually the rate over the number of compounds, because it's going to be the rate, the interest rate you have actually at each compound. So just be careful about that. So the 1 plus r, you're really having to plug in 1 plus r over n. Just be careful about that. So let's say I want to know how much I owe after 4 payments, and I completely forgot this formula that I can just substitute into. I can use the idea of compound interest accruing coupled with subtracting off a monthly payment to find out how much is owed after a certain amount of time. Let's just say for a $100,000 mortgage with a 6% annual interest rate, I have a monthly payment of, let's say, $1,000. Let's keep it nice and simple. Okay. I want to know how much is owed after, let's say, 3 payments. What happens each time that you make a payment is, first, the interest accrues, so you take the amount that's on the balance of the loan, multiply it by 1 plus the rate, which is 0.06, divided by how many times it's compounded, which is 12. So you're adding a 12th of the 0.06. Raised to the first because it's just happening once. This represents the balance of the loan with the added interest, and I'm going to subtract off $1,000 because I'm making a payment of $1,000. That'll give me my amount that's remaining after 1 payments. So 100,000 times 1 plus 0.06 divided by 12 minus 1,000 gives me $99,500. Okay. Now what I'm going to do is I'm going to take that new amount, because that's the current amount owed, and I'm going to do the same kind of process. 99,500 times that 1 plus 0.06 divided by 12, because I'm going to take that balance that I have right now, coupled with the interest, and I'm going to make my $1,000 payments. Okay, so it's going to be times 1 plus 0.06 divided by 12 minus the 1,000, which gives me a balance now of $98,997.50. Okay, and I just keep this process going until I get to the number of payments that I want to find out I'm given. So this is a sort of 1 payment. This is the second payment. For the 4th payment, I just do it 2 more times. Okay. So keep that in mind. There's ways of doing these problems without knowing that formula, that crazy formula. Alright, so thank you for watching this video. This is a summation of all the most important things in this particular unit. From this Unit 5, you should be able to understand the difference between arithmetic and geometric sequences. You should be able to apply, create, and interpret the formula for any type of a sequence, a geometric, arithmetic. You should be able to understand and create the explicit formula or recursive formula for an arithmetic or geometric sequence, and be able to translate between the two. You should be able to find the sum of a sequence of numbers given the sum written in summation notation. So given the sum, summation notation, find out what the sum is going to be. You should be able to calculate an arithmetic series or geometric series. Just recall that the series formula for arithmetic series is not given to you. You have to memorize that. And be able to apply a given formula to find the amount owed or mortgage, but also using that formula to help find out the monthly minimum payments or the number of payments needed to pay off the loan. Alright, thank you for watching. Hope you found this video helpful, and I'll see you in the next review.